Hi, and welcome to today's session on Pragmatic Python. This meetup is jointly hosted between Upskill ML, a meetup focused on empowering technical professionals to solve their organization's most challenging problems, and Data Education DC, a meetup dedicated to democratizing data science within the DMV area. And in collaboration with Deep Learning Adventures, a meetup focused on positive change through deep learning. In today's session, Eugene will be going over part 2 of his Pragmatic Python tutorial. Here, Eugene will explore args and kwargs, decorators, cool built-in functions, and neat Python syntax. Eugene is a full-stack data scientist at a Fortune 100 company, a 4-time hackathon winner, and an open-source contributor to Dask. With that said, let's hear from Eugene.
Thank you very much for the generous introduction, Josh. Yes, this time, this is Advanced Python, Code Like a Pro, Pragmatic Python Part 2. So it's like Pragmatic Python Part 2, it's like PPP2. So that's the stimulus package for the mind. All right, let's get into it. So with Josh's background, intro, it's correct. I'm not a CS major. I don't have the traditional CS background. I can't invert a binary, inverted binary tree or something like that. I don't even know how to use hash maps or heaps and stacks that well. I've only took 2 CS courses. Got a B+ in both of them. Started programming in Python, primarily going through a 3-month coding bootcamp. That's where I started it all. But mostly I'm self-taught. I don't program in academic problems. Those are not interesting to me. But what I can do is I can code in interesting problems, pragmatic problems, you could say. So I'm a 4-time hackathon winner, GCP certified data engineer, consensus certified blockchain developer, distributed computing person. Basically, things that are interesting to me, I will do, and things that are not interesting to me, I kind of avoid. So hopefully, I can teach you something interesting tonight. So it's really not about me. It's really about you and what you want to learn. So in this talk tonight, we're going to cover generators and generator functions, star args and star kwargs, which leads in nicely to decorators, and I'll show you a bunch of cool built-in libraries and some neat Python syntax. So why did I write this tutorial? It's because I want to teach people how to learn Python the easy way, and also for free. Because what happened is, when I first started out, I read a book called Learn Python the Hard Way. It's on the left side, written by Zed Shah. He's written multiple books on multiple languages, and it's basically an all-around know-it-all. It's like basically everything. But he sells that book for $36.58. But we learn Python here, Advanced Python, Pragmatic Python Part 2, here for free. On the right, we have Dave Beasley. He's not a part of the PSF, but he does contribute significant parts of code to open source. For example, he created Curio, which is in some sense a competitor to Async.io. He also was the one that created the try except handling. So it was actually his idea. So he's basically knows a lot. He teaches an in-person course, practical Python programming course for $2,500. He also teaches a follow-on course called Advanced Python Mastery for $2,750. We will cover all that and more over the course of our talks for free. So learn Python the easy way and for free. So if you guys can join me, please join me inside the code and go to this link right here. This link right here provides you to a resource called mybinder.org that gives you basically a free container that you run code in the browser. So I'll give you guys a moment to basically copy that into your browser, and we'll jump over to code.
Hey, could you copy it into the chat, Eugene?
That's a great idea. Thank you very much.
Thanks. I know you've sent it before. I just don't know where I put it.
Here, okay. Great to see you. Where is my chat window? Wait a second, I'm going to stop screen sharing for a second. There we go. All right, so if you guys get the first link, you'll get to basically this website right here. Let me just copy and paste it. So it'll look like it's loading up for a couple seconds. Should take no longer than 10 seconds to load up. So this is what it looks like. And within 10 seconds, we'll get basically free Jupyter Notebooks online for like an hour or two. So if, while it's loading up, I'll give you a preview of what's going to happen. Oh, I guess I need that. So let's go through the first notebook, 1_pragmatic Python. So last time during the talk, we went through halfway. We finished map and filter, like pragmatic functional programming. So we finished all the way up to this section. So the next section is generators. So if you guys scroll approximately halfway, that's where we begin tonight's talk. So with no further ado, let's begin. So what is a generator? A generator, also called a generator expression, are not necessarily functional programming topics, but they behave very similar in that generators are lazy objects that save memory and defer computation. In that sense, generators are an optimization that saves you CPU time and also RAM. So that's nice. So map and filter can also be written as comprehensions, which are generators. I'll give you an example below. So anything you could do with map and filter, you could do with just regular comprehension expressions. Last time I also was using the terms iterator and iterable quite loosely, synonymously, but they're actually slightly different. The devil's in details right here, you can read about it. It's not too important, but what is important is how to use a generator. So right here. So generators, what they do is that because they're lazy, they have instantaneous runtime. So if I run the cell, that's 1 millisecond. That's actually quite slow. If I run it second time, it's very fast. So that's 1 microsecond. So 1 millionth of a second, or 655 microseconds. So 655 millionth of a second. And they also take very low memory footprint. So constant memory footprint. So here I'm looking at the size of this generator object. So that's a generator object right there, and that has a size of 128 bytes, right? So if I increase this to 10 million, it'd still be 128 bytes. If I increase this to 100 million or even a trillion, right, ad nauseum, right, the memory footprint for this object, for this generator expression, is 128, and presumably for also the other objects in memory. Right, so all of them take constant memory and instantaneous runtime. They're lazy in that they have not been manifested. They're just a lazy object to say, what should I generate the next item to be if I want to get the next item? So the difference between a list comprehension and a generator is a square bracket and parentheses. Be careful in that the parentheses, what makes a generator expression is not really even the bracket or the parentheses. It's just this, the actual generator expression is right here. It actually contains no brackets or parentheses. You only put the brackets and parentheses to basically make it syntactically a valid Python. For example, this thing right here is a generator. And I can save that object. So I don't actually need these extra parentheses here. I could just put the parentheses like this, because this is the actual generator expression. Right? They'll say generator object. So it's this thing in between the parentheses that's the true generator expression. Why do we put like brackets or parentheses around it? It's to basically finish the statement, or finish, I guess, interpreting the line. So here, this is a tuple comprehension. This is a manifested tuple. That corresponds to this line right here. So that's an actual getting the elements out, because you're forcing it with the tuple call. Right? Like if I put brackets around here, then I get a list comprehension. So like having brackets or another set of parentheses and calling list would also basically materialize and make the generated expression into a manifested list or tuple or whatever it may be. In this case, this will actually consume RAM and CPU time. Whereas if I just removed the list, it consumes constant memory and very little time. So, and also a tip is that when you're using a generated expression and using some type of accumulation, like some reduced type of logic, you don't need the brackets here. You could just keep it with the expression, generated expression inside the accumulating function. Right? You could also do this with sort. Right? Sort you could also do, like you don't need to sort a list. You could sort a generator expression. And the reason why is that if I did the following below, let's see if this is able to show runtime performance. There we go. Oh, perfect. I didn't make this up. So if I do sum over a generator expression, you get the same results, right? The results are the same. But summing over a generator expression takes less time than constructing a list first and then summing over it. So this takes constant memory. Even if I increase this to like a billion, a trillion, a quadrillion, or so on, it would take constant RAM and time because it's just getting the next element in this range object. Whereas this is a true list. So like if this thing has like range a billion, then you're getting like a list of a billion elements. So that would take a lot of not only time to run, but takes a lot of RAM. So this is actually, in some sense, not scalable, whereas summing over a generator expression is scalable in terms of RAM. So before I move on to generated functions, does anyone have questions on these generator expressions?
So Eugene, the expression where you increased it by 10, you said it's constant in time and RAM.
A constant in, so if I increase this by 10, it's constant in RAM, but not time.
Okay, got it. That's all I want to clarify. Perfect.
Mm-hmm. Does anyone else have any questions? Sure, let's move on to the next section. So generators often we see these as like a 16 one-line expression, right? But we create generators without using like the simple logic. We could add more complex logic and still have a generator come out, actually. So generated comprehensions are very useful. They do map and filter. But what if we have any other logic that does not fit a map and a filter? What do we do? We create a generator function. So what does a generator function do? A generator function, when it's called, will create a generator object, which is, you could think of as the equivalent of a generator expression. Or actually, I shouldn't say that. Let me just give you a real example. So let's say I create here's my generator function. And you can have it take any number of arbitrary arguments. You can have it take 0 arguments, 1 argument, 10 arguments, it doesn't matter. They look like a regular function. The only difference is instead of a return, it has a yield. That's how you determine that this function is a generate function over, let's say, opposed to a regular function. So let's execute this function, and it's just a function, nothing special, right? But when I call this function, it gives me a generator object. So take a look. So it gives me generator object. What type is this object? It's a generator. So what is interesting about this generator object? It's lazy in that it executes 0 lines of this function so far. When I call, like a typical function, when you call the function, right, it executes the body of the function, right? But when I called here, it executes 0 lines, right? How can you tell? Because it didn't print anything. I asked it, the first line of the body says print, but over here it printed nothing, right? So how do I execute the body of this generator function code? I call the next. So in Python 2, it used to be the next underscore and next underscore method, but now in Python 3, it's the next function. So hopefully you guys can hear me better, but let me call next and see what it says. Oh, it says start. Perfect. So it says start. So now when I call next, it starts executing the body of the code until it hits a yield. That is a keyword. When I run next, it will run the body of the code until it hits a yield. So ran print start, no problem. For x in range, in this case, I did range 10. So the first element of x will just be 0. If x modulo 2, so basically, if I get an odd number, do something. If I don't get an odd number, do nothing, right? So if I get an odd number, so the first time x is just 0, so basically nothing happens. So I go back into the loop, and then x is, in the second iteration, x equals 1. If x modulo 2, something, print high. So it prints high here, and then it yields that value. So the return of the next function on the getOdds generator object will return 1. And then the next time I call that next method or next function, it does not start running all the way from the top of the function body. So for a regular function, right? Every time you call the function, it just runs everything again, right? It has no memory of the previous call. But when you call the next function on a generator object, it will actually remember where it is in the function. So the first time it yielded 1. Next time, it can x will be 2, and then it does nothing here. So it does nothing there. So we go back to the top of the loop. I'll say 3. So if x modulo 3 modulo 2, then it'll print high and yield 3. So basically, this thing will yield odd numbers and print it, right? So how do I know it's actually doing that, right? What I could do is I could change the code actually and basically print, value isn't important. So if I reran this again, I can actually see that it will print the value 2, but it returns the value 3. So current value. So what I expect here is it'll print the value 2, but current value will be 3. So as promised, value 2 isn't important. It also prints high, but what is the current value? It's 3. And then you could do it multiple times. Eventually, when the generator is exhausted, it hits something called stop iteration. When the generator is empty, it will raise the stop iteration exception. So how is it hit in our case specifically? I did a range 10 here. So the last successful yield will yield 9 right here, or yield 9. So what happens when I call the next function on top of the generator object after that last successful yield? What it'll do is it'll go back to the top of the loop. Well, it'll finish the loop, and there's nothing left. There's nothing left, so it returns nothing. So like that will generate a exception and basically generate the stop iteration. So does anyone have any questions before I show next step about infinite generators? Oh, so someone in questions asked, how do you differentiate a generator function from a regular function? The answer to that one is simple. That's a simple question. So good question. Easy answer. Great question, easy answer. The only difference is the keyword yield. If you have yield anywhere, even, let's say, even if I put a line that would never ever execute. If false, yield 1. This line will never ever execute. But once I create, call it, it'll generate, it will return a generator object. Oops. There. So the keyword that distinguishes a regular function from a generator function is solely the presence of the word yield, regardless of whether it will ever actually be executed. So does anyone have any other questions?
So is that the only difference? What if, say, we write return? I read a comment that it will generate some exception, but so like, is this the only visible difference you can identify a generator?
Sure. You actually, this is a little fancy. I wasn't expecting. You asked a very good question. I wasn't expecting this question so early. But you can stick a return. In Python 2, I believe you could actually never put a return and yield in the same function. It was an illegal syntax. Python 3 can. So what happens when you stick both of them together, right? So the first time I'll do yield 1, yield 2. The third time, it'll create a stop iteration, I believe. And what it's returned is the message of the stop iteration. In async.io, or there's a fancy tool called yield from, which is technically, I didn't cover it here. Yield, so like there's yield. Python 3 has a new keyword called yield from, where you can actually mix yield and return. You would generally put only, and you can nest generators together, right? So you could put a generator inside a generator inside a generator, and so on, right? So the only time you would naturally ever stick a yield and a return together is on the outermost the bottommost generator. And that's for telling your function how to do some exception handling. So generators also have there's something called a coroutine built on top of a generator that allows you to do generator handling. That's for async IO, asynchronous event-driven programming. In short, you can mix yield and return, but only if you do asynchronous programming. But typically, you would just not use yield and return. You'd either use yield or return, but not both for 90% of use cases. Great question. That was a pretty advanced question. Does anyone else have any questions?
The whole goal of this is for like a lazy function.
Yep, lazy in terms that it doesn't use CPU and it does not use RAM or constant RAM usage. Any other questions?
Hey Eugene, I have a quick question. So, in principle, if there was a case for using a function instead of a generator, what would be the case for using a function rather than a generator? Like, could we create our entire code set just using lazy evaluation with generators?
That's a great question. I have to think about that for a bit, but I think theoretically you can. In functional programming, you can do most things lazily. So I think you probably could do everything in a lazy manner. For example, in Dask, it has actually a lot of things are lazy. Dask is kind of like Spark. So like let's say Spark. Most things in Spark can be lazy. The only exception is like the underlying data that you want to run everything on, but that could even be loaded in a lazy way. So technically, yes, everything actually can be run. You could write the code and create the objects for the final output you want, and then choose when you want to execute it. Great question, Josh. I never thought of that one. That's quite interesting. Does anyone have any other questions? All right. Did I hear anybody?
A more advanced question, but I'll wait for later on.
Sure. Let's go to the next section. So generator is different than a function in that it never has to terminate. You could create generators that go on forever, infinite generators, right? So in this generator, it's actually very simple. You have this while loop that's always true. So it'll always continue going, right? And all I'm doing is this is an incrementer. In the func tool, in iter tools, there's already something that does this. But if you want to implement it yourself, you can actually do it this way. So all this does is it yields 0, 1, 2, 3, 4, 5 ad nauseum to infinitum. Right. So that's all it is. So like you create a generator, and let's say you don't want to start at 0, right? Starting value. You can say I want to start at a let's say I want to start at 10. So then that's simply what it looks like. So generators are different than regular elements in that it could go on forever. Our generator functions can have a loop that never finishes executing. So another use case would be for generating prime numbers. So if you want to keep on generating prime numbers, this is how you could do it. So like yield 2, yield 3, then keep on finding the next prime number. Once you find the next prime number, then just yield it. So this generator goes on forever and ever and takes constant RAM and is lazy. So deferred computation till the point that you need it. So there's a lot of benefits using generator expressions, and generator functions, but there are some cases where you don't want to use a generator. One case is the obvious one where, let's say you have a list, right? You want to read the list forward? You can't do that with a generator. but you can't read the list backwards. You can't even stay in the same place. For example, let's say I want the first element of a list, and you want it twice. That cannot be done with a generator, because with a generator, you can only move forward. You cannot move backwards. You can once you call next, that previous call of the generator basically just disappears, right? That's the double-edged sword, right? It saves memory in that you don't know what the previous element of this generator was, and you don't know what the next element of the generator is until you call it. But that's the downside, in that once you go forward in time, you can't go back in time. It's gone forever. So because of this, you cannot slice a generator, nor can you jump directly to the nth element. If you want to go to the nth element, you would have to go call next like n times, and you get the nth element, but the previous n minus 1 elements are gone. So you would have to save it, the objects, if you wanted to keep the previous next calls. So once a generator is exhausted, the entire state is lost. There's an attribute of the generator that says if it's exhausted or not. So once it hits that stop iteration, it's basically gone. So that's generators. Does anyone have any questions?
Yeah, I had a question regarding the comment that you made about Dask Spark, and also that Josh, when he mentioned that, can you write your entire code base with lazy modules or in a lazy way? I know in regular programming you can probably parallelize your code. You can use libraries in Python that can run in parallel. How does laziness affect parallelism? Basically, can you run things in parallel, and how do you synchronize them?
That's a good question. So how Spark does it is that for Spark, Dask, the Apache Beam, multiprocessing, those are for processes that are called embarrassingly parallel. So things that can be split and separated and done by multiple workers simultaneously. For example, counting the number, getting the word count of encyclopedia is mostly embarrassingly parallel. Not completely. So for example, the simple way I would do the word count of an encyclopedia, let's say a physical book, right? I give everybody, let's say a person is my CPU, right? I give like 10 people, I have 10 CPUs, I have 10 people, right? I give each person a page, and I just ask them to do a word count on that page, right? And then, like, oh, the word the shows up 100 times, the word I shows up 50 times, the word cat shows up 30 times, and so on, right? So that is purely, it's called embarrassingly parallel, because they do not depend on each other. But once everybody's done the word count on their pages that they're responsible for, then they have to accumulate their results together. So like between person 1 and person 2, how many times did they see the instance of the word the? Like, let's say, 100 times. Second person says 200 times. They add it together. So together the encyclopedia has the word the 300 times. Right? So for generators, if you could split the data across multiple generators, then you can call them, you could say, simultaneously. And how async IO does it is they run an event loop with coroutines. So coroutines are just fancy generators, and they're two-way generators. I could show you an instance of it like right now quickly, but the async IO basically runs multiple tasks and starts and pauses generators and switches between them. Similar to multi-threading, but not exactly. It's better than multi-threading, but it's a little hard to write. But even in async IO, you're only using one CPU. It's not true multi-processing. So if you want, I guess, so what Spark does is that it's lazy, but it has multiple CPUs run the job on separate data sets. So suppose you have 10 files, right? 10 CSVs, 10 Parquet files, or whatever, right? And you have, let's say, 3 CPUs. Then each CPU will lazily load these files and then process them. So when you use multiprocessing, you can use generators simultaneously and extract the results. So it's possible.
Got it. Thank you.
So since you asked, what is a coroutine? A coroutine is a fancy generator, generator function. My coroutine. This is used in async I/O, event-driven asynchronous programming. Let's just say it. So this is just a regular coroutine. This is not a, this is so far a regular generator. It's well, actually, technically, a subroutine just a coroutine just generator. Call the next on it, right? And nothing special here, right? 7, 8, 9, then stop iteration. What I can do is something weird. This is very weird because a routine return cannot do this. So this is still a generator, still the same generator type, but well, actually, even the previous one was still a coroutine. I just didn't save it. But this is fine, right? Oh, but it prints something called none. So what if I do send hi? Or sorry, send. It'll start printing hi. What is it doing? What is it doing? Let's take a look at this coroutine. When you have a return, you never save anything because the return just returns. It's done, right? It's executed and returns out of that function. But a yield is very confusing. The execution of this line is right-hand side first. So execute this line, and the yield will yield back the element from the next call, right? But if you do a send is in between the yield and the assignment. It's after the yield, but it's the value of the assignment. So to prove that, I could do something very strange. I could do that. So I'm going to yield the value, but I'm going to, when I send it, I'm going to multiply by 2 and then assign it to this variable. So what will well, this will fail actually. I'm going to send hi, and it should print out hi. Let's see next. So it prints out hi because the yield comes first. So that is the thing executed by next. But when I call the coroutine send method, it reinserts this value back into what was the yield in the line, executes the rest of the line, multiplies by 2, assigns it to something weird, prints it out, goes to the next iteration loop, yields the next thing, and that's when it pauses. So that's where I get the 1. So I got 0 the first time, and the next time I get 1, and so on. So if I send, I think I can't send nothing because none can't be multiplied by 2. But if I send like a list, I'll just be multiplied. This is fine, right? I just get a list multiplied by 2. So all coroutines are technically generators that no one was aware of that feature until they do it. So generators are quite special. You can do a lot of cool things with it, basically. Does anyone have any questions?
Hey, Eugene, can I reset a generator function or do I need to recreate it?
That's a great question. When you finish the when you've exhausted the generator, it's gone. So you have to create another instance of that generator. Yeah.
Thanks.
Mm-hmm. Does anyone have any other questions? All right. Let's get to the next very juicy topic: star args and star kwargs. A lot of people have seen it. They see it in Matplotlib a lot, like everywhere. And like people have no idea what it means. But so today I'll show you what it means. But I want to preface with this. Let's just start off with star args because that's one that's easy. But I want to preface that where you see star args impacts what it actually does. That's actually very confusing when you see it for the first time. So I'm just going to show you examples first and then explain it after the fact, right? So I'm just going to go through examples first. So when you see star args in the function definition or signature, right here, when you see star args here, it gathers all the arguments together and puts it into a tuple. So here I'm calling the function and I'm putting some arbitrary like stuff in it. None, high, by, great, false. What star args does is it gathers all these positional arguments. So it will come in that order. These are positional arguments. And it'll create a tuple, which you just see here. It's a tuple. And to confirm that's a tuple, I just print type. And it says tuple. So star args will be a great, it gathers all the arguments here and makes it in tuple. That's all it does. But however, when you see star args in a function call, not in a function signature, it does the opposite. So in a function call here, I'm putting star here, not in the function definition, but in the function call, it does the opposite. It splits the arguments. So in this case, you could have a list, like it just splits it up. So like technically you could use not just a tuple, you could use a list. So list, you could probably even use a set, probably. You just lose the order of it, probably. I'm not really sure, but I'm pretty sure you could do this. I'm surprised the set orders could maintain. But set orders are not guaranteed or anything like that. You could even technically, if you're kind of weird, you could even put a list in here. It'll iterate over the list, or a dictionary, and I think I'll get it out. Oh, perfect. So basically, but let's just do what normal people do, and not this insanity. So most people just use a list or tuple. Probably a list because the list is mutable. But in the function call, when you put star in front of an iterable, it just separates the argument into the arguments here in that order. So like ABC, I print out ABC right here. So that's why I print 1, 2, 3. So how can I prove that it does it in that order? I could print C, B, A, and so instead of saying printing 1, 2, 3, it should print it in reverse. So basically, at a high level, star args in the function call splits up a single object, well, a list, a single object is one list here, single tuple or whatever, into multiple elements to fit the function signature, and use it. Whereas when you use star args in the function definition, it absorbs all the arguments and makes it into one tuple. So they just basically do opposite things in different places. So let's say I am required 3 arguments here, but I only put 2, right? Then it will complain that I'm missing my 3rd argument. That's how I can also prove that's doing that order, because it fits 1, 2, and then it can't find argument 3. So it can't find C, so it fails. So what you could do is you could just do comma 5, and then you're totally fine. So, and you don't even need to use like the star args in the beginning. You could use it anywhere. They're all just positional arguments. So you can put it at the end. So star just means split. That's all it means in the function call. So does anyone have any questions of star args before I go into star kwargs? All right, let's go into star kwargs. Basically, it's the same thing, but for dictionaries, keyword arguments. So star kwargs in here means gather all the arguments, keyword arguments, and make it in a dictionary. So I'll be printing a dictionary, and to confirm, I'll print the type of it to say it's dictionary. So I'm gonna call this. It says, oh, the variable a. So this is like a here, but it becomes a string here, value here. So like some limitations of this is that you can't have the key be a thing that's not a valid variable name, right? You can't name a variable 1, right? You can't say 1 equals 2, right? 1 cannot be a variable name, right? So I can't make this 1. I can't even do 1 as a prefix, right? So like I could stick like a1, that's valid, but I can't do 1a. Right? So that's not a valid variable name. So all it is get the keyword arguments that are not absorbed by the signature. So let's say I put something here. So then kwargs will absorb anything that's remaining. So A is totally fine. It won't absorb A, so it'll print B and C and put it in the dictionary. That's all it does. So star args makes it into a tuple. Star kwargs makes it in the dictionary. So just like before, when you put star kwargs in the function call, it separates them. And it does not require position, the correct order, right? Like a dictionary is like unordered, right? So like if your signature requires ABC and you put it backwards, it's totally fine. It'll figure out the correct, like it's essentially equivalent to this. So, so star kwargs in the function call will separate your one element, which is the dictionary, into all the necessary variables arguments here. Does anyone have any questions of star args before we move on?
I have a question. So
Yes.
relating to the same, when I see in Python language, when I see an asterisk or that star sign next to something, does it always mean packing and unpacking, or does it depend on whether it's related to args and kwargs or not?
All the time I think when, like it could be interpreted different as like when you use one star, it means multiply, right? So like, 5 times 1, then star just means exponentiation. 5 squared is 25. I can't think of any other use cases. There is, so like this thing is an operator. It's an operator. So like you could technically make the star weirder. So let's say if I want to do, so the simple answer to your question is that most times for variable unpacking, wouldn't use it this way. The complicated answer is that you can make star really anything you want. For example, operator overloading, Python, let's see, I think that's just multiply or something like that. Silly. Silly int class. See if I can get this working. Live coding, guys. Let's see if I can get this working. really sure if this is going to work, but let's try. So, oh, thank goodness it worked. Live coding, I could still pull it off. Like, I created this class called integer that inherits from like the regular int, but I've overwritten the regular multiply. So I've kind of messed up, or I've changed how the star operates on instances of this class. So when it's called operator overloading. So that's just overriding the method. So like everything you do in Python is basically a method call. Like pretty much everything, every object in Python is really a dictionary on the hood, even integers, even floats, even booleans are really dictionaries on the hood. And anything you do, like adding a number, multiplying by a number, dividing by a number, even adding, if you want to add like booleans together, those are methods calls. There's a method on the true object that allows you to do that. So like if you overwrite these methods, and in this case I didn't override add, I override multiply, which is represented by this star operator, then I could change the behavior. So like, 3 times 2 is like 6, right? What I did is I overrode it and I just did something funky. I multiplied by an extra 2. So that's how I get 12. So like, if you wanted to, you could override the method corresponding to star or star to do whatever you want. So like, that's a long answer, but the short answer is that 99% of the time you just do star and star, like either like multiply or exponentiation, or for like variable unpacking.
Gotcha. Thank you.
Question to Ishan's. Yeah, I think what I understood is that the star operator is used as the unitary operator when there's no left-hand side argument. It's just the right-hand side argument. Is that only for list packing and unpacking, or is it used for something else? I think that's what I understood.
Oh, that's a good way to phrase it. In that case, if it's purely unary, I think it would probably just be only for unpacking. Yeah, I think you're correct.
Okay.
That makes sense. Thank you.
Mm-hmm. No problem. Does anyone else have any questions of star args and star kwargs before we move to the next section?
I had a question. Sometimes a very popular error in Python is when you have default values for arguments in a function. So let's say you have a function and a equals something, that's the default value. Then when you call it, there's some limitations on how you call it, right? You cannot have pre-assigned variables, or pre-assigned variables has to be first. There's some limitations that I always forget.
That's right. Yeah, so let me just show you that exact point you're mentioning. It only allows you to put default values at the end. It does not allow you to do default values in the beginning. So like you can't do this. Like this would fail. Yes, you're correct. Yes.
Got it. So that's just like a syntax limitation, I guess, right? Or restriction.
Yeah. Oh, now you reminded me. You actually can stick star somewhere else. This is in new Python 3.7, I think.
Oh yeah, I remember the picture.
Forgot how you do this. That is now also a valid syntax.
Hold on.
What it does, I have to recall this. I think this one forces you to name the argument. So I think you can't do. I think it might mean you can't do any star here. I forgot. But it's in 3.7 or some new version of Python. So like, you have to check to see like what it actually means. But I guess that's another use case of star.
But if I compare it to other languages where star usually, for example, C or C++ means, like you're actually operating with memory. This has nothing to do with that.
Correct. This is not, this is not like dereferencing or like array extraction. Yeah.
Cool. Thanks.
Good question. Good question. Does anyone else have any other questions before we move on? All right, then. Let's combine star args and star kwargs. So this is the one that most people see. So we built up to this point because otherwise it'd be very complicated to explain and understand what's going on. So you can have a star args, then a star args, and I think you could technically reverse the order because it kind of, I think, doesn't matter. Let's just actually try that. I think we do this. Oh, I guess not. I guess not. Oh well. So, but no one's ever seen that style syntax anyway. So, this is the syntax you see: the star in front, single star in front, and a double star in the end. And technically, you could put some more arguments in the beginning too. So, yeah. So like, like you could put named arguments that you care about, and then this, type of stuff afterwards. And also, as a quick tip, is that args and kwargs are not special words. They're not special. You can name it anything. You can call it my silly args. You call it the silliest, not silly. Like the let's see. Yeah. So like args and kwargs are not special words. You can put them anywhere. You can use anything you want. So what this does is that the first star captures all the positional arguments that have no argument name. So like these things have no argument name. And the second star in the function signature gathers all the keyword arguments that do have a name. So D, E, F, right? So that's how I could know. So this thing becomes a tuple. So I gather in that order. So I get the silliest. And then the second thing I print is the dictionary here. So D, E, F. And technically, dictionaries don't have any order until Python 3.7 guaranteed it as a implementation of the language. So like actually, in Python 2, everyone said that dictionaries are not ordered, or they're pseudo-random ordered, or they're in a unsorted order or whatever. In Python 3.7, dictionaries are actually ordered. So you are guaranteed order of the dictionary when you insert, and even after you delete an object, it's still in that order. So, or what's left of it. So, but for the most part, before 3.7, even before technically midway through 3.6, dictionaries you could consider unordered. But anyways, let's see. So the star in the function signature gather arguments together. But when you use star in the function call, it separates arguments. So this 1, 2, 3 will become A, B, C, and this F, E, D to basically show you that order does not matter in keyword args, but does matter in these positional args, prints DEF, which is 4, 5, 6. So if you want to be fancy, just use stars everywhere. It's a constellation. There's, 6 stars here. So you get a star, you get a star, you get a star. Everyone gets a star. So this is kind of ridiculous, but it's possible. I gather my arguments here, put it in a tuple, gather my arguments, keyword arguments, stick it in the dictionary, but I have no, I guess, technically positional arguments or keyword arguments in the function call. I just do it here. So like, you can put stars everywhere, basically. And the neat thing about that is that it leads to the next topic, which is decorators. So before I move into like the decorate heavy section, I guess we should take a break. But Let me just give you this quick example. So this decorator does nothing special, takes an argument, gathers any arguments during the function call of that argument. So I'm just going to do the decorator sum, new sum, range 10. Behaves totally normal. So it gathers any arguments in keyword arguments and then applies it to the function like normal. So the reason to learn star args and star kwargs is really to learn decorators. But before we get to the next section, we can take a break. But before we take a break, does anyone have any questions on star args and star kwargs? All right, in that case, let's take a break. All right, welcome back to Advanced Python, Pragmatic Python Part 2. You guys are with me? Let's head into sections for decorators. So, what are decorators? It's that thing that people talk about, but no one understands, or a lot of people don't understand. I remember when I was an intern many years ago, and some advanced programmer said, "Oh, Eugene, just use a decorator." And I was basically too afraid to ask, what is a decorator? Like, I had no idea. I thought decorators were things you put on Christmas trees. But it's actually not that complicated. It's actually very simple. But here's the boring academic definition. Like stuff that a professor would tell you. Maybe Professor Josh would tell you this. But decorators are higher order functions that either take in a function and or return another function to compose more sophisticated functions. What that really means in real life is we can make our existing functions cooler. We're going to make an existing function that we have cooler by changing the behavior before the function call, or after the function call, or even slightly during the function call. And I'll explain to you what that means. So basically, you could change your function. And why would you want to use a decorator? Why would you want to use a decorator? Because you can't change the original function because it's too complicated to understand. For example, like let's say someone else's function is just 1,000 lines of code, and it's like, oh, this is too complicated. I'd rather change the thing before the function is called or after the function called, but I don't want to actually change the function. The second thing is that you simply can't change the original function. You can't change the function because NumPy functions are written in C. For example, let's say you want to change the function sum. The function sum, so let's say I create a silly function. I could inspect it. I can inspect it. So I can see, oh, silly, what is that? Oh, here's my doc string, some args. So I can inspect it, right? I see my args and my doc string. But I cannot see that for builtins. Builtins, I can't see how it's implemented. It's a built-in. For example, import inspect. I could actually see the source code. I can see the source code, and I can even get the byte codes for this operation, which is, how do I do that again? This. This assembler shows you how to, what the function actually is doing. So this is what the function is actually doing for this function here. But for if you want to disassemble like the built-in, let's say sum, cannot be done. Can't be done for things that are built-in, which are like or C extensions like Python. So things that are written in C, the built-ins, cannot be inspected, cannot be changed from the source code. So that's another reason why you would use a decorator. You can't use another reason. You can't change the original function because you don't know where it's used, and you only want to change it sometimes. So sometimes when you call it, you want to have change behaviors. Sometimes when you call the original function, you want it to stay the same. So like, oh, how can I change it when I want to, when I feel like it, basically. So like that's when you would use a decorator. And lastly, when you just want to be a pro Python programmer, that's when you use decorators. Just show off to other people what they don't know. Let's show an example of a decorator. So decorators are nested function. It looks like this type of structure. This is the decorator. You put a function in there, and by magic of something called closure, you get the function here. And let's just go with an example first. Let's see what this does. Okay, so in this case, here's just a regular function called double. It just doubles your number. Just a regular function. Nothing magical is happening here. Next, I'm going to apply the decorator onto a function, right? Typically, we apply functions to data, but you can apply functions onto other functions. So I'm applying this decorator function to the function I want to be decorated. What does it give me? It gives me yet another function. How do I prove that? I do type. Boom. I proved that I got another function back. So what is... someone asked me closure. Oh, did I mention closure? Yes. The function is closed over. So George asked a very good question. Well, what do I mean by closure? That word is not too very important right now, but I pass in a function double. So this func is double, and then I return inner. So I don't return func, I return inner, which I just, by seat of my pants, just return this function I just created. But what is closure? I'm putting func here, but I don't have func in the function signature. So where is func being defined? It's being defined here, or rather outside and being passed in. So the function is closed over. So that's closure. Not too important right now. I'll talk more about closure in functional programming. The notebook here. That talks more about closure, but the word right now is not too important. But basically, a decorator says you change a function before the function is called or after the function is called by passing it in to a different function. So let's take a look at how this works. So this is my regular function here. All it does is double. I apply this decorator on top of the function, so I get another function. And since this part is just another function, I could call it. So I call it with number 42, and it returns like double, right? So nothing special here, right? So this is what I mean before and after. So before the original function is called, I could do something. I could print, I could start a timer, so I could runtime profile this call. So like if I start a timer here in the beginning, and then I do calculate the time here after the function is called, then I could calculate how long that function took. I could change and sanitize the arguments. So like if the argument is something, I could change the arguments. And after the function is called, I could like close a connection, close a resource, print something, whatever you like. So that's what I mean by doing something before the function is called and doing something after the function is called. And what I mean doing something while the function is being called, I'm kind of using that word loosely. What I meant by that is just like changing arguments here. So like args times 2, or maybe adding in another argument. I'm just gonna hard code in like another argument or something like that. So like that's what I mean when I say like changing the function while it's called. Using that phrase a little loosely there. So, all right. So like, how do you make this change in the function permanently, right? So I've defined this function. All it is still just regular double. So like all it does is multiply the 2, right? Let's see if I can get that docs source code out. right? It's still just a regular double function. Nothing fancy is going on just yet. But what if I want to make this change permanent, right? I take in the function, pass it into the decorator function, and I get out another function, and here's how I make it permanent. I store the function as what it was originally called. You could call it something else. You could call it double func or whatever, right? You can name it whatever. But this double is no longer this double. This double is a transformed double that follows the logic of whatever I put in my decorator. So like now it's decorated. Whenever I call double, it has that new behavior, right? So before the function is called, I print hello. After the function is called, I print bye, and I save. So in between, I save the result, and then after that, I return result. So that's why it returns the number 2 and 6 here. So I've permanently changed the behavior of this function double. But this syntax is kind of ugly, right? It's like, well, you're throwing a function into another function, and you're saving it as this function. Like, how do I know this function? Well, that's because I could do type. But like someone would get confused, right? They say, well, this looks like just a variable. Like, maybe it looks like data. How do I know it's a function and not data, right? So then I changed the syntax to make it that way. Here is the preferred syntax that makes the decorator function applied to the function permanent with nicer syntax. So no, like most people don't use this syntax because it's ugly. This is how you do it like a pro. This is how the pros do it. It's syntactically equivalent to what was just done before earlier. Just it looks nicer. Yeah. So there we go. So like when I applied the ampersand, the @ to the function like this, then it's automatically decorated. So does anyone have any questions before I move on to a more practical use case?
For decorating, is it just that sign that's important? You can write anything after that, kind of like the args kwargs thing.
So like after the and sign is the decorator function, and so it's getting advanced, which is the section below. You jumped it. You can actually put arguments to decorator function and then also apply that to this function. So like this decorator function can also take arguments if you want. Does that answer your question?
Yeah, thank you.
Sure.
Question I had is, you said this is a good idea if you want to do something before or after a function, Eugene. You said that you can also do something during a function call. Is that a more advanced example, or?
Yes.
Did you share that already?
Yeah. Let me repeat like what I meant by during the call. When I said during or while the call, I'm stretching that phrase a little bit. What I really mean is like you're changing something in the function call here. So like if you hard coded in a number, or you multiply, like you've changed the what you pass in the function at call time can be changed like in line here. That's what I meant by changing the function during the call. So I'm stretching it a little bit. That's what I meant.
Thanks.
Mm-hmm. All right, so let's go to a practical example. Let's see what this does. All right, let's just run through. So penalize type. So in this case, I want to sanitize my variables or arguments, right? So let's say like I intended this function to be only run on numerical values, numerical data, right? Strings and ints, ints and floats. Not even booleans, because you could double like a boolean, like times 2, a valid operation. But let's say I restricted it to only floats and ints. This is how I do it. I'd create a this is my decorator. that I'm applying to my double function, and I basically don't allow it to take anything other than floats and ints. So this func will be double here, right? So when this is a function that's actually being returned here. So run it. So double will say, when you print it out, display it, it'll say inner. Inner. That's referring to this thing that's being returned by the decorator function. It's returning a so this decorator is returning this function that is just defined here. So when you're calling double here, it's actually calling this function here. So let's say I call double 42 here, right? Arg is now string 42. String 42 goes here, fails it, raises an exception, complains, and that's what you see here. If everything's fine, return the original function and its call. So if I do string 42, totally fine. String 42.2, totally fine. But when I do bool, it fails because that's not what. Oh boy, that's not good. Oh, I forgot. What? Do you guys have guess why that actually succeeded? I'll give you the answer here. The Boolean type actually inherits from the integer type. It's actually the bool is a subclass of int. That's why. So like when I put a bool in, it accepted that. So that's why it worked. So if I did string true, then it would fail. So that's not allowed. Okay, great. So someone had a great question. Neil has a question about how do you use the pro decorator notation on a ready defined function? Well, unfortunately, you can't. so like the pro style of using ampersand is only valid when you are just defining the function. Otherwise, you just have to use the ugly style. So like, let's say you're decorating a function that you imported, right? Like, let's say you import like pandas and use some pandas function, right? Then you just have to use the unpro, the ugly style to do it. So that's how you do it. Yeah. Hope that answers your question, Neil. So that wraps up the section on decorators. There's more cool stuff in the fourth notebook, Functional Python, which all about decorators, all about functional programming, all about lazy validation, all the cool stuff. We're on the first notebook, but there's so much more ahead of us. So does anyone have any questions on decorators before I move on to helpful libraries?
I didn't fully get the type MRO. What was that command that you typed? What did you?
MRO is a method on all classes. Let's see what other class? Well, I mean, any class has MRO. Like if I make silly class inherits off of, is there any fun classes? I can't think of any fun classes. MRO means method resolution order. That's actually, that's a great question. In the third notebook, in object-oriented Python, I go over what MRO is. But MRO at a high level stands for method resolution order. It deals with multiple inheritance. And the specific algorithm that solves MRO is C3 linearization, which came from a paper about a language called Dylan. So Python inherited features from another OOP language called Dylan. But MRO just basically tells you what are the parent classes. And all classes inherit from object, right? So object is like the God class is what's his name? David Wouters is like one of the core contributors of Python. He calls object the God object. It's like everything goes back to object. every method call I also believe goes up to object. Is that true? That might not be true, but object is the God object. It's everywhere and everywhere, but it cannot be like when I say delete, I can't delete it because it's not defined, but it's there. So object is one of those like cool things in Python that is everywhere but also nowhere.
And your decorator, when you were checking for specific type, you're checking for integer or float. The Boolean worked because Boolean is a subtype or subclass of int.
Exactly. That's exactly what happened. Bool is a subclass of int. So when I put a bool here, like true or false, this is actually, it is actually an int. So this condition's false, so it actually runs this.
Got it.
So if you wanted to, this is like a way you can make your functions like pseudo statically typed. It's not truly statically typed because it's not discovered at compile because there's no compile, right? There's no compilation in Python. It's all interpreted, right? It's at runtime. That's when things will fail and inform you. So like this is how you can make it kind of pseudo statically typed language if you want to make Python.
One last question, Eugene. What if you want it to be explicitly float oriented but nothing subclassed? Could you limit that?
Yes. So let's say I want int, right? And I don't allow. This is a question I myself Googled myself the other last week. You have to manually do it. You have to do this. And now this is not but true. Now Phil. So if you want exactly that class, you have to do it this style.
And if you have a list of allowable.
Yeah. So then, if you want a list of allowable, like int and float, but not bool.
Got it.
There we go. So you can do anything you want. Like it's all in there. Python's cool.
Nice. Thank you.
Right. No problem. No problem. Thanks for the question. All right. Let me see if I can cover. Well, does anyone have any questions on decorators before we blaze through the rest of this notebook? All right, let's go through helpful libraries. These are cool libraries that I use, and I wish I knew about them when I first started Python because that would make life suck less. Because Python has batteries included. Everything, a lot of things you want in Python already built in. Like when you're in school, copying people's stuff is bad. It's plagiarism. It's like, oh my gosh, you're unethical, whatever. In real life, copying code is a pro. That's what you do as a pro. If you did not copy code and you actually implemented it yourself, you're doing it wrong. So use other people's code. They did it for you. Just borrow what they do. So what is the collections library? Collections makes your regular data types that Python gives you, like dictionaries, lists, tuples, everything, even cooler. So like when you have a regular dictionary, you can make that dictionary cooler. If you have regular set and tuple, you can make them cooler. But there's like name tuple, there's a frozen set, there's probably something with list, but I don't know right now. But dictionaries are the ones that I'm interested in. Let's make our dictionaries cooler. Roque wrote a message in chat channel about why use other people's code. Why not to write your own code if someone else already wrote the code? So you watch that YouTube video. But let's go ahead with, let's see. Okay, so this is how to do things the painful way. This is actually how you do it in early Python 2, before the advent of collections module. Collections was created by Raymond Hedinger, core Python developer. But before Raymond created the collections, this is how you do it. So let's say I just want the letter count, word count, but for letters. I just want to count the letter number of times each letter appears, right? The way I would do it originally in Python like 2.0, ancient Python, grandpa's Python, your grandpa's Python, is that I have a dictionary. If the letter is the dictionary, add 1 to it. Otherwise, I create an entry in dictionary and initialize it to 1. It's like, oh wow, I mean that's literally how I did it when I was in school. Like I didn't know about the collection, so that's the literal way I did it in school. I thought, wow, Python sucks, man. Why would anyone do this? Then I learned the cool ways. So let's do it as a pro. So instead of doing in a dictionary, you could do a method called get. So get gets given a key, get the value in the dictionary if it exists. If that key exists in the dictionary, get the value. If it doesn't, get this default value. So for first time, let's say I go A, right? A, for letter and letter. So letter is A. A is not in this dictionary, which is just an empty dictionary meaning. So let's just write it literally. So here's my dictionary. I get A, doesn't exist. If I do A dot get dictionary dot get A, then it returns. It always succeeds. It never fails. And the default value is none, but we can change it to anything we want. So get 0. So in this case, I never have to check if I don't have to test for membership anymore. I don't have to test if a key's in a dictionary. I could just get whatever I want, assign it to the dictionary after fact. So this is how I shrink this if-else into 1 line. So what was 1, 2, 3, 4 lines is now 1 line. But we could do one even better. I could do it in 1 line. So when I use counter just does it for me. Basically, counter is just this logic. I don't know if counter is written in C or in pure Python. We can take a look. Let's see if I do inspect. Oh, I guess counter is implemented in Python. Or let's see. Well, I actually can't tell. I can't tell if. Oh, it is. It is. So here's the little source code for dictionaries or the counter object. So like it's in Python. So like it basically just wrote this code for you. So that's what it is. So counter counts the elements in an iterable. So it could be a string, it could be a list. So if I did a counter of like a list, it counted for me. And then there's methods attached to dictionary, like most common. So like I could get the most common, the absolute most common. So it gives me 1 element, which is this one. Or if I don't put it in, it'll just give me all of them. So like it'll just sort them. It'll sort them. So it gives me the most common, second most common, third most common, fourth most common, and so on. Let's see. And it behaves like a dictionary in pretty much every other way. So instead of even the for loop, using the counter class, you could just do it in 1 line. So radically simplify your stuff. There's also another, so like for MRO, right? Method resolution order, you can see that indeed that counter inherits from dict, So any counter object, counter instance is a dict. So this is true. So that's what it is. But let's say you have there's something also called default dict. And you could tell this was written a long time ago. Do you know why? Because it doesn't capitalize doesn't capitalize the class, right? Right? Like if you think about it, right? Dict, list, tuple. It must have been written a long time ago because they do not capitalize these class names, right? They're lowercase. Whereas counter it seems to indicate counter is relatively new and default dict is a little older because they capitalize counter but lowercase default dict. So that's kind of like a syntactical bug in Python, right? But whatever. So the important part of default dict is that you can specify the default values for non-existent keys in the dictionary. So let's go through what that actually means. So like here, I just create an instance of the default dict. Sorry. Yes, that's true. I create an instance of the default dict. Oh, so this thing is just the default dict, right? Then I access a key, but this key doesn't exist in the dictionary yet, but the value is already available. Why? Because I set the default value to be list. So that's a list right here. And then what I could do is I could always append, or like I could get the value immediately and do whatever I want. So because default value is a list, I could always append to it immediately. So that's how I get this here. So default dict is very useful. So to initialize a default dict or instantiate a default dict, I need a callable. So here's my function that whenever a key does not exist in the dictionary, I call this function. So if you want to do something fancy, this is how you could create a counter with a default dict. So int, when it's called, it just returns 0. So a default dict of this of any key is just 0. Oh boy, let's try. There we go. It's 0, right? And then I'm able to, so this one, first instance of this call will be 0 plus 1, store it back into the dictionary itself. So this is how I can create a counter using default dict. And the default dict is callable. It takes in the callable, right? So you could define your own function. So you could define anything. So it doesn't have to be int, it doesn't have to be a list. It could be any callable you want. So like anytime a key does not exist in the dictionary, it calls this function. So I think I could append to it immediately. The nice thing is that you can still do tests for membership. So if a key does not exist in the dictionary, it will still return you the correct answer. So the key B is not in the dictionary. In fact, I've actually had to use this in real life. I had a default dict and a default dict where the default value is list. So it's a dictionary within a dictionary where the value is a list. So it's a real life thing I actually had to do in real life, so that's possible. So that's explanation for the collections module, which is like advanced, cool improvements over the regular data types. Next thing is TQDM. It's the creator of TQDM pronounced it Takadam. That means progress. It also means I love you so much in Spanish, apparently. But it's a progress bar. And what I like about it is that it prints out how much time has elapsed. And this is a prediction of how much time will remain. So this is just prediction. So it could be wildly wrong. So the left-hand side is accurate, like real time. And the right-hand side is a prediction based on what it's expected before. So this is a nice way to time your functions. I use it quite a lot. I like it. Here's PDB. It stands for Python Debugger. The better version is IPDB, which is IPython Debugger. Python, I think 3.7, 3.8 has something called breakpoint. So I think this one has it. So I can call it breakpoint. And I get the debugger. Usually I just use print statements everywhere. I use print statements to find the status or the state of variables, arguments, so on. But when it's super nested in, and you can't print your way out of this problem anymore. Like you can't figure out what's wrong with the code. Use the debugger. This section shows the debugger. I hope that you'll never have to use it. But if you ever have to use it, the section tells you how to use it. let's just go quickly over what the remaining time we have here. 3 minutes to cover this part. So inspect lets you get the source code of a function. So let's see. Let's define this flawed function here and get the source of it, source code. So here I'm putting the source code of that function. So that's a neat thing to do. And you can even print source code of methods, classes. You can print source code for a lot of things that you're interested in. Here's another thing: is dir as a function. It's built in. Dir by itself tells you what the global variable scope, global variables are. So like these things are all defined in my interpreter or right now. So like this thing is currently defined, and like these weird things are also currently defined. So let's see what it is. That. So, but if you do dir on an object, it gives you the attributes of that object. So remember, everything in Python is actually a dictionary, and I want to inspect a dictionary and see what it is. So this range object gives me all these things on the hood. So that's what dir does. It gives you the dictionary under the hood. OS, that's not too important. Let's just quickly go through Python's string interpolation. So there's like 3 styles, like now 4 styles to do string interpolation. So like old styles %s or %d or something like that. I personally don't use it because that's a very C style. I tend to use format. And the new style is f-string. And there's actually a 4th style called templating, which I don't really know how to use. But 3 styles I use format the most. String interpolation, blah, blah. Oh, so for what's really cool about f-string is that you can nest f-strings together. So you could even do this. So like you can nest an f-string. So f-string just allows you to evaluate the thing, the variable, and inside a string. So the first name is just a string, last name is just another string. So if I put f as a prefix, I forgot what f stands for, but once I put f, then it evaluates it. So like if I do nested f string, you get something crazy like that. So that's pretty wild. Context managers. Well, since we're out of time, I'll leave you to read back context managers and implicit line continuation and string concatenation. Blah, blah, blah. Let's see. Anything else here? Here are just some interesting resources. This is actually the article that prompted me to write this advanced tutorial. This is the article that shows like different Python styles. The author is Nick Coughlin, who's a core Python dev. And here's an article by Thomas Waters, a core Python dev, that explained the magic behind Python. So if there's any questions, feel free to ask. Otherwise, Josh, we can wrap up.
So we'll just wait a minute for folks to type questions in the chat, and after that we can wrap it up.
Yeah. So if you guys have any questions, feel free to ask me, or also just type in the chat. But before we go, let me whet your appetite to the next talk. So we've covered all of Pragmatic Python, right? That was the first notebook. Let's get you a sneak peek of the next talk, which is procedural Python, mastering control flow. So most people have seen, this is a big topic, expression versus statement. Most people have seen pass, break, continue, if, else, else, for. But most people haven't seen for else, and most people haven't seen while else, and a lot of people don't know about try, except, else, finally, and also creating context managers with try, finally, and a case statement. So those will be topics we cover next time. But if anyone has, any questions about this notebook, feel free to ask.
I had a question about, where was it? Oh, back before you started with the helpful libraries, I guess this was box 7. We were talking about decorators, and you had the penalize type function. I wasn't sure why, at least in the handout or the original version, why does double of 42 not work?
Oh, sure. Double 42 as number works, but string 42 does not work.
Oh, it's just, okay, thank you.
Yeah. So like if I put like a number here, it works totally fine.
Got it, okay. Thanks.
Super. Thanks so much, Eugene, for walking us through this. Really enjoyed learning about kwargs, args, and decorators. It's definitely areas that I've come across when I've been programming, but certainly not this level of detail. So very excited about that. But again, thank you so much, Eugene, and definitely looking forward to the next one.
Thank you very much, Josh, for inviting me to talk, and thank you all for attending my talk. I hope you really enjoyed it, and hopefully you'll join us next time and as we go through procedural Python.